So in this lecture, we're going to be looking at the order parameter and phase transitions, how to describe phase transitions, the different types of phase transitions there are, and also the kinds of theories that have been used to describe them. This is a really large topic, and we're just scratching the surface of it, but it's a very interesting and important topic. So this man here is Volker Heine, and I'm giving these lectures in 2020. I'm making this recording in 2020. And I think he's still around. He tried to teach both myself and a large number of undergraduate students at Cambridge about this kind of thing when I was a graduate student. I don't think he really succeeded very well for any of the students, but at least we all got introduced to the material, even though none of us became experts on it. And that's all you can really hope for at a university course. You can be introduced to various things. Becoming absolutely expert on them in the course is not possible, but at least you know they exist, and that's important. Okay, so what are we going to do? This lecture is about phase transitions. What kinds are there, and how do we make simple models of them? Which do not involve the nightmare of partition functions. So you've all been introduced to partition functions, and that's the exact way of doing system mechanics. And there's a machinery there, which in principle you put in your system, you crank the handle, and out comes the answer. Unfortunately, the crank of the handle is not trivial. And for most systems, we can never really properly analyze them in terms of partition functions, even though they do give us the right answer. So the idea is you try and short circuit things and come up with simple approximate models which give you lots of information but don't involve the horrible nightmare that is the partition function. And that's what we're going to try and do here. So, phase transitions and order parameters. That's what we're going to do. Phase transitions, order parameters. And we're going to start off with talking about order parameters, and then in this particular lecture we'll go on to do some mathematical preliminaries. So, what's examples of phase transitions? Well, they're all around us. Freezing of water, cooling a system to make a ferromagnet, cooling some iron, for instance. Cool it below the Curie temperature, becomes a ferromagnet. Liquid crystal transitions, the transitions which are used in liquid crystal displays, maybe the one you're watching now, in fact. So, for instance, the simplest one is you have a system of rods here, so-called pneumatic phase, whole system of rods. At low temperatures, those rods will line up, okay, and at high temperatures, they'll start to point randomly due to entropic effects, and you'll have them pointing all over the place. So there's a pneumatic, so-called pneumatic phase, and an isotropic phase, and it's going from an order here, this is order, and this is disorder. Okay, so that's an example of a phase transition. Always, if you have a display, it's going to be in this phase. If you go into this phase, your display will cease to work, and that you can do by hitting the thing up enough. Okay. So this is an example of a transition between order and disorder. Okay. You can also get transitions between different kinds of order. So I told you before that there are all these different phases of ice. Let's look at two: ice 1c and ice 1h. Now this is ice 1c here, and this is ice 1h just there. And you can see they only differ very, very slightly. If you look, for instance, at the top of this, you've got the this particular atom pointing out towards you. Here, it's pointing away from you. But here on the base, both of them are pointing away from you. So these two geometries are actually slightly different. On the left, we have a cube octahedron. On the right, an anti-cube octahedron. Okay, so the right is ice 1h, which is almost all the ice we see in the world is that ice, and a little bit is that. Okay, probably different pressures and temperatures and things like that. You'll get different kinds of ice. Okay, but that's the transition between two different kinds of ordered phases. Okay, so that's order transition. So in order to describe these kind of things, we need to introduce an order parameter, which I'm going to label as phi here, which describes how ordered the phase is. And I'm going to be really vague about exactly what this phi is. Very, very vague. Okay, it might be a scalar, like the density in a liquid system, or it might be a vector, like the magnetization, or it could be a tensor, like the strain in an alloy, or something like that. So it can be many different things that are going to be really vague, really, really vague. Okay. The reason to make it vague is because then it's more general. Okay. Magnetic dipoles. Okay, so that's an example here. Ordered phase in a ferromagnetic phase. Okay, so if you have high temperatures, suppose you heat a bit of iron, to 5,000 degrees or something before it melts, all the dipoles in the iron will point randomly. Okay, and if you look at a small patch, there's random pointing. Okay, if you cool it below the Curie temperature, they all start to line up in one direction. Although you get domains, so some of these other ones will line up over here in a different direction, but you'll get domains where it's all ordered. And the order parameter in that case, the natural order parameter is the magnetization, which is the magnetic moment per unit volume. So that's a typical case of an order parameter. It's the one you should probably think of in your mind when you're thinking of order parameters. That's a very typical case. Let's do a separate system to that. Suppose we have a system in a volume V with a certain number of green particles and a certain number of yellow particles, N yellow and N green. Okay. Now, entropy would encourage mixing. So entropy would encourage the system to look like this. Okay. But enthalpy might oppose this. The energetic interactions might oppose it. For instance, in the case of oil and water, that's what happens. Okay, you get an opposition between these two effects, and you might get phase separation. So at low enough temperatures, we expect to get something that looks more like this. Maybe in fact complete phase separation into green on one side and yellow on the other. But this is a system which you can have phase separation in. Okay, so how do we describe this system? Well, we could use a density here. So let's define the average number densities would be N green is the number of green molecules per unit volume, and N yellow, N yellow is N bar yellow is the number of yellow particles per unit volume. And our order parameter could be, not necessarily be, but could be a scale difference in number densities, i.e. the number of particles per unit volume, averaged over a small volume. So we take a small volume here, and we start counting how many greens and how many yellows there are. And we can define this to be our order parameter, which is the number of greens divided by the average number of greens minus the number of yellows divided by the average number of yellows at some particular point R. So here's my point R. R there. Okay. So when phi equals 0, we have perfect mixing. We have n number of greens is equal to number of average number of greens, etc., etc., etc. And when phi is greater than 0, we have more green, which indicates separation. So we could have something like that as an order parameter, as a possibility. What's important for order parameters is that they have, they describe the order in the system for a start, and it has the correct symmetry for that system. So if we go back, for instance, to a pneumatic system, pneumatic doesn't distinguish, where's the pneumatic? Here we go. Pneumatic systems don't distinguish up from down. So our order parameter can't, for instance, be a vector. Okay, and that system goes up and down here. That direction and that direction are the same. So you've got to have the right symmetry here. Whereas in the magnetic system, where are we? You can have an order parameter which is a vector, because up and down means something different in this system. Okay, so that's what I mean by symmetry. That's a quite subtle point, and we won't go into that much here. We can also let our order parameter phi vary in space. So it varies as you go around the place. So the order parameter here is different than the order parameter there. Okay, and x is often a vector position, but we're going to leave it as x just for simplicity. Okay, as I say, we're being very vague and very general. Okay, this means the theory we're going to present has very broad applicability. It not confined to some particular system like pneumatic systems or magnetic systems or phase separating density systems. All right, now we're going to do a little bit of mathematical preliminary work, because we're going to need to use some functional calculus here. We're not going to do anything very heavy in functional calculus in this particular course, but it's good that you're introduced to it, because some of the language that's used to describe these systems is in the language of functional calculus. And it's a little bit like general relativity. Most of the people watching this video are never going to use general relativity, ever, okay, in their entire lives. However, it's good to have seen it for 20 minutes, So you can then say, okay, I understand a little bit of that. It's good to have seen some things, even though you might not use them. Okay, and this is true of functional calculus, which most of you will probably not use outside of this course, although some of you who do quantum field theory, for instance, or some advanced classical mechanics might use some of this stuff. So let's do functionals in their calculus. What do we mean by function? Well, let's go back to what we mean by a function. You've all known what a function is because you've all done it several years ago in mathematics, and you probably understood it very well. You were probably towards the top of your maths class, and that's why you're doing physics now. Okay, so a function maps one set of numbers onto another set. That's what a function does. You've got this set of numbers here, and you've got this other set of numbers here. And if you want to know what the function here, this one is mapped onto whatever it is, 2.5 or whatever. And in particular, for a given argument, it gives us a number as an output. So a function takes a number and gives you another number as an output. So, for instance, the function f of x equals sine x. If you take, if we give it pi on 2, it will give you another number as an output, 1. So you put a number into a function, you get another number as the output. That's what a function does. So that you're familiar with. Okay. What is a functional? Okay. A functional is something different. It maps a function onto a single number. Okay? And that's a weird concept, but it's a concept you're actually completely familiar with. Okay? So, suppose we have a function 5x. We've got some function, doesn't matter what it is. We define a functional j. This is our function j, functional j, sorry. And it's given these little funny brackets around it just to tell it's a function. And a functional of this function 5x, phi is the input, and the output is the integral from 0 to 1 of phi of x dx. That's how we defined it. Okay, we defined our functional j to be this. So that's the definition of our functional j. It takes a function, j at 5x, and, which is there, and it outputs a number, one number only. So it takes a whole function like sine of x, or doesn't matter what you do. Okay, so let's take sine of x. So let's take our function as sine of x. We plug in sine of x, we do an integral from 0 to 1 dx of sine of x, and we get that. And that's the output. So sine of x gets mapped on to that. If we put in x squared as our function, the functional maps it on to the integral of x squared between 0 and 1, and it gives us a third. Okay, so again, we've taken a functional which maps this function onto one number, and one number only. Okay, so that looks a bit odd, but that's what a functional is. Okay, so, and you're actually quite familiar with this. So, for instance, the functional for the area under a curve. This function, so you want to find the area under a curve between 0 and 1, this is the functional you define for the function phi. So the functional is j. You put any function into that. Here's our input, and the output is that. Okay, so that's the one we just defined, and that's the area of the curve between the curve y equals 5x and the x-axis between 0 and 1. Okay, and we give this functional a curve, that's input, and it gives us one number, the area. Okay, that's the output of our functional, one number. Takes a whole function and it condenses it down to one actual number. Okay, another example, functional for the volume. Suppose we have to take some curve like this. We rotate it about the x-axis, say between 0 and 1 again, just for fun. And we want to find the volume of that surface of revolution. Well, the volume of the surface of revolution is just pi times phi squared dx, and that's another functional. Again, we take a function phi, and the output of the functional is a number. Okay, so that's what a functional does. Right, now we could have more sophisticated functionals, more complicated ones. We could take a functional k, which takes the integral between 0 and 1. I don't have to take this integral between 0 and 1. This could be 0 and 150, or 5 and 150. It doesn't matter. Okay, it wouldn't matter what these things are. I've chosen 0 to 1 just for fun. We could take a functional of phi, which looks like this. It takes the integral of phi squared, and then it also has d phi dx squared in it as well. That would also be a perfectly good functional. Okay, a functional is often an integral. In physics, they tend to be integrals, but they need not be as long as it evaluates to a number. You could take a functional of phi, say p. Is this equal to the value of phi at x equals a half? That would be a perfectly reasonable functional. Very boring, but reasonable. Even more boring. P of phi is 0. That's another functional. Okay, these kind of functionals don't normally have them much, but you could have them. So where have we seen these before? If you've done some field theory, quantum field theory, classical field theory, whatever, you might have seen them before. You've almost certainly seen them in Lagrangian mechanics, even though you might not have called them functionals. So, for instance, the action of a path for a particle with the coordinates q of t between times t1 and t2, you have to know q and q dot. The action is the integral from t1 to t2 to t of the Lagrangian of that. And S is a functional which takes the position function q of t and gives us a number. Okay? And the path taken by a classical particle minimizes this action. So there's different kinds of paths you can take, but the one that minimizes the action is the one it will take. Okay, so you might have met functionals in that context without actually calling them functionals. Okay. Now, we've got functionals. Who cares? All right, I've defined a functional. You might think, well, what's the point of that? Okay, what can we do with them? Well, we can differentiate them. So let's go back to differentiating a function rather than a functional. So given phi of x, how's the derivative defined? Well, this is how you define the derivative. The limit as delta approaches 0 of phi x plus delta minus phi of x divided by delta. In other words, you all know this from calculus. You go back here, you've got some function of y equals 5x. Some function y equals 5x. Here it goes up here. You take 2 points, you separate them by delta. This is x plus delta. And then you take the difference between the two phi's here, there and there. Divide by delta, that gives you the slope. Okay, so that's the practice you do to get the derivative. Okay, make a small change in x, small change delta in x, and find out what the change in phi is, and divide by delta. And that's the end. Okay, that's how you define the derivative of an ordinary function. What about functionals? Bit more complicated as you might expect. Okay, so to define the derivative of a functional j of phi with respect to phi, that's what you do. You're not differentiating with respect to x, you differentiate with respect to phi. Okay, now we can write this as little funny delta j phi of x d phi of x, or just sometimes without the x, doesn't really matter. Okay, how do we define the derivative of a functional? Okay, well, we go back to what we did for a function and do it analogously. Okay, so we take our function, which might look like this. This is phi of x. Okay, and we add to it an arbitrary perturbing function. So we take this and we might perturb it a little bit by, this is not a good picture. Let's do a bit of picture, and let's add to it, this is phi of x, and let's add to it a little extra bit, rho of x. So this is phi of x plus epsilon rho of x, where rho is some arbitrary function and epsilon is small. So we add to phi a little extra bit, which is epsilon times rho of x. Okay, so here you can see that here. Phi of x plus epsilon times rho of x. Okay. Then we subtract off the original bit we had, the original functional j of phi of x. We divide through by epsilon, and we take the limit as epsilon goes to 0. And that, of course, is the same thing, if you think about it, as dj d epsilon, using ordinary calculus, okay, at epsilon equals 0. Okay, and then we say that is equal to the integral over x of the derivative we're looking for times rho of x for all rho of x. Okay, so this is a quite complicated definition, but it's an algorithm you can follow, in fact, for anything. Okay, so this is the definition here. This defines the derivative. We define the derivative by doing an integral, and then we do dj phi plus epsilon rho d epsilon at epsilon equals 0. And that gives us, ultimately will give us this thing itself here, although it's not clear from this slide that's true, but let's go for some examples. Okay, let's do a typical example. Let's find the derivative of this functional, the functional derivative of this functional here, j, which I'm going to define as the integral of phi cubed. Okay, so first we form j plus epsilon rho, where rho is arbitrary and epsilon is just a very small perturbation. And of course we just get that. That's not interesting. Okay, then we use ordinary calculus. We find dj d epsilon, and that in turn, of course, you can just bring it down here to j d epsilon, and we get the 3 going down here. We get the rho going down here. We get phi plus epsilon rho squared. So all I've done is differentiate that thing under the integral sign with respect to epsilon, and I get that. Okay, and then I take the limit of phi plus epsilon, j of phi plus epsilon rho d epsilon, which is with the limit of that as epsilon goes to 0. So that bit goes away, and I'm just left with that. Okay, so that's the right-hand side of this definition here. So that's that bit there. Okay, just there. Right, so I've done that. That just involves ordinary calculus. That's actually straightforward. Okay. And our functional derivative formula now tells us that that right-hand side is equal to this. And this guy here is the thing we want to find. dj delta j delta phi. How do we get that? Because it's hidden inside the integral. Okay. Well, the point is that this rho is totally arbitrary. Any rho you choose, this has to be true. And I think you probably met this kind of thing when you were dealing with Lagrange's equations. If you try and derive Lagrange's equations, a very similar kind of methodology. So rho of x is arbitrary, and the only way this equation here can always be true is if this guy here, the guy we're trying to find, is equal to 3 phi squared. That's the only way. Think about it for a long enough time, you will see. That's the only way that can ever be true for all possible rho. And so now we have found the derivative. Okay. So this is the functional derivative of j. Note that it's not a functional. It's now a function. So the functional derivative of a functional is actually now a function. You're getting out 3 phi squared x. Okay. Now that shouldn't be any surprise, because for instance, the derivative of displacement is a velocity, not a displacement. So the same thing is happening here. Okay. Derivative of functional is actually a function, at least in this case. All right, so you might want to go away and stop the video and try a couple of problems yourself. I've written them down here. Let's take the functional j phi of x, which takes the function phi of x and gives us the area between it and the x-axis, between x equals 0 and x equals 10. So show that the functional derivative is 1. Or do the same thing where you take the functional which gives you the volume of revolution between x equals 0 and x equals 10, and you should better show that 1 on 2 pi times the functional derivative gives you the function itself back. Okay, so go away and try those two, and then we can move on to the rest of the video. All right, so let's do another example here, a more complicated example. Often in physics, we have a squared gradient in our functional. So a squared gradient, in other words, that thing. Okay, it's like kinetic energy or bending of a beam, all that kind of stuff. There's those kind of expressions. So this is a functional again, but it's an integral of a squared gradient derivative. Let's try and get this. What do we do? Well, we do dj phi plus epsilon rho d epsilon. If you do that, you will get this as your answer, plus some non-negligible terms. Go and do that yourself. Take the limit epsilon goes to 0, you will get this. Okay, so we end up with saying, well, not going to end up with anything yet. Now we're going to integrate this by parts, because you can see this has a rho dx, and I'd like to get rid of the rho dx and express it just in terms of rho if I could. So integrate by parts, I'm going to get this kind of expression. Okay, and now obviously I've just got a rho there. And usually this part in physics goes away because of the boundary conditions. Either phi is fixed, in which case rho must be 0 at the boundary, or maybe do phi dx is actually 0 at the boundary as well. Okay, so you can have either of those two or some mixed boundary, but normally that would go away, maybe 0, and you're left with that term. And so now we have this as our expression, and we need to find that. And the only way that this expression can always be true, this expression here for all rho, is if dj d phi, the functional derivative of j, is equal to minus d squared phi dx squared. I shouldn't really have that there. It should be. It's possible to write that way, but it's okay. I suppose it's okay to write that. All right, so that's our functional derivative. The functional derivative of this thing here, our squared gradient, gives us a negative second derivative term. Okay. All right, so the applications of that to mechanics are fairly obvious. If you have the action x of t as a functional position of x of t, so you're getting a particle in 1D in a potential, so we only have x and we have some potential looking like this, for instance, and here's our particle moving around. We have the action, which is this thing, integral of Lagrangian. Lagrangian for this system is easy. It's just half the mass times the velocity squared, the kinetic energy term, minus the potential energy term to get the Lagrangian. And S for this system is minimized over all possible paths between A and B, starting at time t and ending time tb, which is that thing. So I'm going to minimize it. And to minimize it, we take the functional derivative. Okay, so we're starting with the action based on Lagrangian. We're going to find the functional derivative set equal to 0 to minimize it. And what do you know? What do we get? We get that equation there. You do it yourself and you'll find that's what you get. You get Newton's equation, which is very helpful, satisfying that you get something which is sensible. Minimize the action using functional calculus, you get Newton's equation. Okay. Other applications. Well, pretty much everything you do in physics can be written as a minimization of a functional. You do that in mechanics, you do it in quantum mechanics, electromagnetism, fluid mechanics, optics, thermodynamics. Just about everywhere you can minimize functionals to get your results if you wish to do that. And sometimes that shows you something interesting. Sometimes it shows you what you already know. Whereas in this case, it showed us what we already knew. But it doesn't mean Lagrangian mechanics can't tell you some new things. But in this particular simple example, it's just telling you what everyone knew already. Okay, we'll finish that lecture there and go on next time to looking at functional integrals, which is even more fun. And we're going to look at those in less depth because the plain fact of the matter is there's almost no functional integrals you can ever do. Whereas